Hello everyone. Today I'm going to be talking about sedimenting and isotropic particles in turbulence. I'm a PhD student at JNCSR and with Professor Ganesh, and this work was done in collaboration with Professor Samriddhi at ICTS. So the first question is, why should we study such a problem? And the motivation is a natural one in this case. So the cirrus clouds which occur very high up in the atmosphere, they are primarily composed of ice crystals. Now these ice crystals, they scatter the sunlight, which in turn affects the Earth atmosphere radiation budget. So the amount of light scattered depends crucially on the orientation of these anisotropic ice crystals, and which makes the study of orientation dynamics of such particles an important problem. So these ice crystals that I just mentioned, they occur in several shapes. They can be thin plates or they can be column shaped. So the ice crystals which are like thin plates, they can be modeled using an oblate spheroid, and the column shaped can be modeled using a prolate spheroid. So in our study, we consider spheroids of all the aspect ratios ranging from slender fiber to near sphere to thin discs. So the problem consists of a dilute suspension of ice crystals, which are modeled as either prolate or oblate spheroids. And they are immersed in a homogeneous and isotropic turbulent flow field. And the entire suspension is acted upon by the gravity. So in atmosphere, these ice crystals are usually micron sized, while the Kolmogorov scale of the atmospheric turbulence is millimeter sized. This I'm talking with respect to the cirrus clouds. So these ice crystals are sub-kolmogorov in nature, and so below the Kolmogorov scales, these particles see turbulence as a fluctuating linear flow. And this is important. So this is what I've tried to show here, that particles actually see a linear flow instead of actually seeing the large scale eddies. So since the particles are sub-Kolmogorov, the Reynolds number based on the shear rate is by definition less than 1. And we can use, so the particles are acted upon by the Stokes track in addition to the force due to gravity. And this is the force balance. In the torque balance, we have two major components. And so this contribution was the one calculated by Jeffrey. And this is because the particle sees a fluctuating linear flow. So we can use this equation. This term is the new term that we have added to the equation. And this is the gravity-induced torque due to the small but finite Reynolds number at particle scales. This was calculated earlier in our group by Vivek and Navneet, and previous works in this field have neglected this contribution. So this is the showstopper in our case. We performed direct numerical simulations for these parameters, the Kolmogorov-Froude number, where here tau p is the particle relaxation time, and we have the Stokes number, the ratio of these time scales, the settling Reynolds number, which is less than 1, the aspect ratio, and we quantify the strength of the turbulence using the Taylor-Reynolds number. So one thing to notice that all the parameters considered for this study, they are relevant to the atmospheric scenario. Because particles in turbulence can occur in a variety of fields, but the simulations are for the atmospheric cases. And an order of magnitude analysis indicates that we will get a dominant gravity-induced torque. We consider 10 to the power 5 particles in our computational box for each run. So I first present the most basic result, the orientation distribution of the ice crystals in their dilute suspension. So for the oblate spheroids, we can see that the orientation distribution peaks at cos theta is equal to 1. meaning this orientation, where the axis of symmetry of the spheroid is along gravity. So this tells you that at small but finite RES, the settling Reynolds number, we have a peak in the broadside on orientations of these oblate spheroids. The inset shows what would have happened if we had neglected the settling Reynolds number. In that case, the peak on the orientation distribution would have been at cos theta is equal to 0, the long side on orientation. So we find that there is a qualitative change in considering non-zero settling Reynolds numbers. Similarly, for prolate spheroids, we have a peak at cos theta is equal to 0. This is again the broadside on for prolates. And yeah. So these results are for R lambda of 150. So that's a pretty strong turbulence. For R lambda is equal to 47, where the turbulence has weakened now, we see that the qualitative results are the same, as in there is a peak at cos theta is equal to 1 for oblates and 0 for prolates. However, the spread of the distribution from this peak has significantly reduced. Here, it spanned the entire phase space. However, here, the peaks are pretty sharp. This is just 0.965. This just points to the fact that turbulence is weaker, so all the particles are expected to be broadside on. And so here we make a comment that these distributions, they are strongly non-Gaussian, especially for oblates. So we'll come to this in a bit. So in conjunction with the numerical simulations that we have done, we also develop a rapid settling theory in the limit of high Froude and low Stokes numbers. So in this limit, there is a dominant gravity-induced torque. So in this limit, the particles are expected to have a broadside-on orientation, and there's a quasi-static balance between the gravity-induced torque and the turbulence torque in the plane normal to gravity, like this plane. And so this automatically implies that the orientation of the particle or of the oblate spheroid will be characterized by this. P3 is the component of the axis of symmetry of the spheroid along gravity. So P3 would be nearly 1, and the other components will be small. So using rapid settling theory, we calculate the orientation of the spheroid as linear functionals of the velocity gradients, basically the rate of strain tensor E and the vorticity tensor S. So here a note, from previous works, we know that and the velocity gradient statistics, they are dominated by the dissipation scales. And due to the dissipation range intermittency, those statistics are non-Gaussian in nature. So this brings me back to this comment that distributions are non-Gaussian. So we expect that because these statistics are non-Gaussian, the rate of strain tensor and the vorticity tensor, so the orientation distributions that we get will also be non-Gaussian. Towards that aim, we calculate the second moment of the orientation distribution using the rapid settling theory. This second moment goes as Froude eta power -4. This is, and we calculate the fourth moment. As expected, it goes as Froude eta power -8. So the prefactor here in the fourth moment is a function of both the aspect ratio and R lambda. This R lambda dependence arises because of the dissipation range intermittency that I discussed earlier. And the second moment, the prefactor is just a function of aspect ratio, not R lambda. So first is we check in the limit of high Froude numbers our numerical results with the theoretical predictions. So we find that in the limit of large Froude numbers, we do get a very good match between the simulations and theory. And as Froude eta increases, there is a deviation in the two results. So this is expected. And so this is the second moment comparison. Similarly, we compare the fourth moment values, and the trend is similar. So same, at high Froude numbers, there is a good match. Here you can see that at high Froude numbers, some points, they don't match well. And this is because the fourth moment of the orientation distribution depends on the tails of the orientation distribution. So the tails we have to resolve by running simulations for a much longer time, which we haven't done. So that's why there is this disagreement. So now we define a flatness factor, which is the ratio of the fourth moment to 3 times the square of the second moment. For a Gaussian, this factor is 1. And we can see from the theory that this factor is much larger than 1. This is for R lambda 200. So we can see that this factor is much greater than 1 for oblates. And for prolates also, it's quite high. This reinforces our initial assumption that the orientation distributions, they are non-Gaussian, and we indeed find it so. So the next, so now we consider the question of the settling velocity of the particles. So the first is the comment on the matching. So for high Froude number, we can see that there is a very good match between the theoretical and the numerical values. However, there is a discrepancy on the low Froude number side. So we can see that the DNS values are higher than the theoretical ones. But why is there such a discrepancy? So we'll find out now. So if for this case, for a high Froude number case, if I plot the concentration field of the particles, we can see that it is fairly homogeneous. For a low Froude number, and for a low Froude number case, the concentration field here is actually, it's not homogeneous. Due to preferential sweeping, there is clustering happening in the different parts of the flow field. So how one can understand this, if you just look at the cartoon here. So this clustering is happening because particles prefer to be in the down-moving regions of the eddies. As you can see, as the particle moves sediments, it mostly wants to be in the down-moving portions rather than the upflowing portion. So like in this curve, for the case of preferential sweeping, the red curve denotes the down-moving portion and the blue curve denotes the up-moving portion. So the density for the red curve is higher than the blue, indicating that, yeah, this is the reason for the clustering that is happening here. Here, there is no clustering because both the curves almost overlap. So it's expected that here it will stay homogeneous. So we try to quantify further the clustering that has happened via a pair distribution function. We take 2 cases. This case has Stokes number of 0.4, which is pretty high. And for this, we find that the pair distribution is non-uniform. It is much larger than unity, the values. While for lower Stokes numbers, this red curve, the pair distribution, it stays uniform throughout. So this again reinforces, because there is clustering happening, the local number density is quite high, very close to the particle. And because it's homogeneous, they're close to the particle or far from the particle, it doesn't matter. It stays uniform throughout. And this is for prolate spheroid. The previous results were for the oblate spheroid. This is for a prolate spheroid. Similar theme. For high Stokes number, we get a non-uniform concentration field. And for low Stokes number, it's uniform. So this is all the analysis for the spheroid. I'd like to end my talk by emphasizing that now we are working on the orientation dynamics of ellipsoids, where we plan to see how the QR space is sampled and similar things.
Any questions?